All right, we're going to do one more lecture on some additional topics on potential. Some of these we've seen in practice problems we've been doing in class, but worth kind of summarizing in a quick video. So let us start with a kind of rapid run through of some of the equations we've been talking about, and again making sure we're trying to connect them back to concepts. We defined potential as a change in potential is connected to a change in potential energy divided by the charge that is moving and experiencing that change in potential energy. Again, remember the goal being that we're trying to come up with a formulation where I can say something about the agent that is making the charge move that doesn't require me to specify exactly what that charge is. So if I can say something about potential, that's saying something about the environment, where then if I put a proton or an electron or a nucleus or gold atom nucleus, I can then from that calculate kind of the motions, the changes in energy, what have you. So we defined potential to be we connected a change in potential to be the change in a charge's potential energy divided by its charge. That essentially got rid of the charge, and then the expression overall only depended on the electric field that the object was moving through. And then we were able to essentially define that in terms of, you might think, if this is only really talking about the electric field that the object is moving through, we should probably be able to write delta V, not in terms of potential energies and charges, but in terms of the electric field, and maybe the path you're moving through that electric field, which gives us this formulation. This could even be a way to define the electric field if you thought potential was the more fundamental quantity. As a change in potential is negative this path integral involving the dot product, over some path that you're traveling. And we got there essentially by considering energy and work-like arguments, where for a conservative force, and the electrostatic force is a conservative force, we can define a potential energy function, U, a scalar, such that it is defined that the work that force does is equal to negative the change in its potential energy. And again, the negative sign connects to, then that allows us to write things like the total energy kinetic plus potential, right, doesn't change overall. That negative was really just a definition, or added, solely for definition. But then the physics is again remembering that it's only changes in potential energy that have any physical meaning or relate to work. And why is that important? Because of the overarching work energy theorem, which connects that doing work on an object results in a change in its kinetic energy. And it really just all starts with the work energy theorem. Combine all these together and you can come up with an expression that an object's kinetic energy changes must involve its charge. That makes sense. We're talking about the object itself at this point, and what kind of change in potential it experiences, which again, this kind of is the object itself, and this is related to the environment which it's moving through. Based on definitions of work, which is an integral of F dot dr, and knowing that the force through the electrostatic force is Q times the electric field, we then can come up with an expression like this. Either kind of the fundamental definition of potentials change when you kind of move through an electric field, or, since similar to potential energy, we can define a reference point where we're going to say that's where V equals 0, just like how that at that reference point we say that's where the potential energy equals 0, because again it's only changes that matter. It doesn't matter and what the exact value of V is. Really, only it matters is what the delta V is. And so, but if you wanted to ascribe a value of V at every point, then you need to define your reference point where you're going to say V equals 0, and then you can evaluate this integral out to any point you're interested in, your point of interest, and that gives you the value of V at that point. This is kind of how you get potential from electric fields. You can imagine if you think of the derivative as the inverse of the integral, you can imagine taking some sort of vector derivative on both sides. One that is involved in this case is called the gradient, and you can then imagine getting some expression for how the electric field is encoded in this scalar function, not a vector v, but if I do a particular vector operation to it, namely take the gradient and then throw a minus sign in front of it, that then gets me back the vector electric field. Again, kind of cool that the scalar function actually has encoded within it, as long as I know which mathematical operations to do, a vector expression. But my life is much simpler if I can just write down scalar functions instead of dealing with vector functions. But if I need a vector function, the electric field, I know how to get it back. And this is very much connected to kind of the energy version of this, which again, this is focusing kind of on the electric field. But in general, this is a general expression for a conservative force. That force can be written as the negative gradient of its potential energy function. So, we started talking about equipotential lines and did some problems related to equipotential lines in class. And these are lines where V is a constant, where if I trace out all the locations where V is a constant, that defines an equipotential line or surface if it's a 3D, if I'm looking in kind of 3D. And these are very analogous to contour maps. So if you look up a contour map, if you go to a state park, that might have some trails, or you're aiming to climb a mountain. You can look at these contour maps where it draws lines of constant elevation, where this particular line are all the locations in maybe that state park that are at the same height above sea level. And then this line is all the points that are at a different elevation above sea level. And so then if I were to say, that these contours are separated by 50 feet, right? This might be sea level, this might be 50 feet above sea level, 100 feet, 150 feet, 200, you get the point. So then I can see, this kind of gives me a 2D topographical map of what actually is going on in 3D. A couple things to think about, when you see graphs like this. Because again, there's information encoded in this. The density of the contours is giving you a sense of the magnitude of the slope, right? If we think of elevation contours, where I could ask myself at, let's do purple, why not? At this point here, which direction should I move to descend the fastest? Well, if you notice, there's a lot of contours kind of squished in that area, and if I know that as I go from contour to contour, I'm changing by 50 feet, that means that I only have to go a little distance in this direction or a little distance in that direction in order to change by 50 feet. Obviously, if I go in this direction, I'm not changing my elevation at all. That'd be a change of 0 feet. Similarly, if I went up in this direction. Versus if I'm out here and I want to know how do I change my elevation the fastest, you might want to say, well, the minimum is down here at the bottom, so maybe I'll just draw a line that points to the minimum, and that would be incorrect. Particularly because if you zoom in right here, you can notice that if you draw a line that just points from that dot to the minimum, you're kind of going along the direction kind of parallel to that contour, at least at first. So at first, if the idea is I need to change my elevation the fastest, it doesn't seem like you're really changing your elevation very fast if you start by walking along in a contour at a constant height. Your height's not changing at all. So you might be able to argue, in this case, that it makes the most sense to locally always go perpendicular to the contour if you want to change your elevation the fastest. So here, that makes sense that you kind of go in this direction. The goal here is that I want to go down the mountain. Here, it makes sense that I go in this direction. You notice these arrows are not really pointing towards the minimum. So you might think it seems like some of these arrows won't get you down the mountain at all. But again, we're looking locally. I could of course zoom in and instead of drawing contours every 50 feet, draw a contour for every foot. And I'd have lots of detail. And you would notice that at each of those locations, that will descend me the fastest, and then after I take one step, I look around and find kind of the contour, I see what contour I'm then on, and then make sure I move perpendicular to that. Then after I take one more step, look at the contour I'm on, make sure I'm moving perpendicular to that contour, etc., etc., etc. And you would trace out some path that would be your descent that would get you down the mountain the fastest. At every step, you're trying to get down as quickly, you're trying to change your elevation as much as possible. That kind of is a conceptual hand-wavy way of arguing that as long as you move perpendicular to the contours, you're changing your elevation the fastest. And then the density of the contours says maybe what is the magnitude of that change. Again, I pointed out kind of here, since if you imagine taking one step, or 50 feet in one step would be extreme, but you can imagine taking a few steps to get down here, you're changing your elevation very quickly. Where here, you might not be changing your elevation super quickly, but you would nonetheless be changing your elevation. Because if this is a particular height, and then this is the next contour drawn, that means that all this region here has to be lower than this contour, but higher than this contour. So you are nonetheless changing your height as you move down that way. But here, you can imagine the derivative, if I were to write this as a derivative, maybe if I use h for height, I might say dh by ds is large, maybe here, where s could just be kind of the direction I'm moving, right? It doesn't necessarily have to be x or y. I don't necessarily have to fix a coordinate system to me, but I'm moving in some direction x or s. Right, I could even use, since we're talking about derivatives, but we could kind of just use kind of bulk delta h over delta s, something like that. So then if I zoom in, this kind of region right there, right, is some length delta s, then I could calculate what is my elevation change over that length delta s. And that would be an estimate of my derivative at that spot. And that would be different compared to, say, here. But nonetheless, at that location, that's where my derivative would be maximized. And these arrows are particularly pointing from high to low, as I go down. So I guess moving perpendicular to contours kind of gets you high to low. The fastest. We could essentially do the same sort of argument with potentials. Potential, we've seen now, is connected to the electric field in some meaningful way. So if I had a potential topographical map and I asked what is the electric field, we could argue that the electric field must point perpendicular to equipotential lines, or these contours. And we could actually be a little bit more physical in thinking about why that might be the case. If I'm a charge that's in an electric field, moving in the direction of the electric field is necessarily going to do work on me. I'm going to speed up or slow down depending on my initial kinetic energy, or whether I'm moving with the magnetic field or with the electric field or against the electric field. But moving parallel or anti-parallel to the electric field will do work. Versus if I move perpendicular to the electric field itself cannot be doing any work on the charge. So if you think of along an equipotential, the idea is if I take a step along an equipotential line, then delta V is 0. That then requires that I'm that then we'll see in a second, that then will imply that I must be moving perpendicular to the electric field. So then that gives me a justification of how to draw the electric field lines. Let's think of this in the calculus context. This is the definition of some sort of bulk change of the potential. I have some path, I have some starting point for the path, some end point for the path, and then if I calculate this dot product along that path and add, for every tiny little step I make along that particular path, which might be windy, it might be a straight line, that path could be anything you dream up, that will give you your change in potential. Again, what you're doing in the calculus context is you're adding up all the little E.dr contributions for every little step. If you think of every step as a small little calculus infinitesimal step, each one you're in some way moving dr, parallel, anti-parallel, or at some angle to the electric field, so you can compute that dot product for every little step you take and then add them all up, which of course the integral is a fancy calculus way of saying add it all up. Right, so for a small, what I really mean is infinitesimal. Right, for a small infinitesimal, I'll say step. What I really should say is for a displacement. Sorry, I ran out of room. Displacement. For one of these little steps along this path, what that's saying is I would expect some small change in my potential is then negative electric field dot dr, right? For one of those, for one step. And then for every step I have a negative E dot dr, I add them all up. That's an integral. And then that gives me the bulk delta V. Right, V end minus V initial, where this gives me my little dV of, for every individual step. All right, so you might say this is per step if we want to stick with this kind of anthropomorphic where the charge is walking through the electric field. And then again, I could of course connect this back to forces and work by multiplying both sides by Q. So then it looks like Q dV equals negative QE dot dr. Q dot dV, if you go back up to our expressions, looks like it's going to then be some small amount of work that's being done. We define that as, not skip steps. Right, we define that as some small amount of change in the potential energy of that charge as that charge moves through the electric field. But then Q times E is the same thing as the force that's resulting from that motion. And then a change in potential energy we defined as negative the work that's being done by that force. So then there's a negative, so then this is the same thing as negative a small amount of work that was done equals F dot dr. And then of course then I essentially just went backwards in my definitions. Right, that this obviously then connects to that force doing a small amount of work on that charge. Or really all I had to do is multiply by Q, which we assume is some non-zero number. So if dV is 0, i.e. you take a step along an equipotential line, that suggests that E dot dr is 0. So it could mean one of those are 0 or both are 0. But again, we're talking about we took a step. So the dr is not what's 0. That doesn't mean E is 0. Right? Obviously that's a way to do it, right? If there's no electric field, of course, there's nothing to do work. It then just must imply that E and dr must be perpendicular. So if E is non-zero and dr is non-zero, then the way to make this consistent, then E dot dr is 0 when E is perpendicular to dr, i.e. E points perpendicular to equipotential surfaces. The negative sign simply says that which direction does E point? It points from high to low. Implies that E points from high potential to low potential. Something we've seen, but again, it's nice to kind of connect it back to the drawings and kind of conceptual ideas. So again, if I go back up to this kind of contour map, if I were on to draw the electric field at particular points, I would point it perpendicular to the contour, pointing from high to low. And again, the magnitude, the strength of the electric field at that point, would then be related to the density of the contours. How much does the potential change? Delta V. In the sense, if we just think of it as kind of bulk quantities, a delta V divided by a delta S gives you and there's a negative sign thrown in there for direction, gives you a sense of the magnitude of the electric field. So that was one point I wanted to make, of kind of connecting some of the stuff we've been talking about with these contour drawings and equipotential surfaces. Equipotential surfaces are going to play an important role when we get to capacitors and circuits, which is the next unit. I think everyone in class was able to more or less derive the potential for a point particle, but let me sketch that out real quick, just to make sure we're all on the same page. So let's do V for a point particle. So I have some Q, which may be positive or negative. I'll draw some electric field lines as if it's positive. If it's negative, we just switch the direction of the arrows. All right, so that we know there's some electric field that radially points outward. We know that electric field is KQ over R squared. And actually, let me be careful. Be consistent with the notation we had in the previous chapters. I was like KQ over the magnitude of R squared times R hat, where this vector R points to some point of interest, some arbitrary location from the charge Q. And moving forward, I'm just going to put the charge at the origin, but again, it doesn't have to be. So nothing new here. So then, if I wanted to figure out the potential, well, just by the drawing, if we just got through this, thinking through this, that electric field lines must be perpendicular to equipotential surfaces. And by the circular symmetry, or the radial symmetry, if you think 3D, I should expect that equipotential surfaces are circles around this charge, or spheres around this charge, where each one of them would be perpendicular to all the field lines moving through it. Now, if I wanted each potential line to be, the same sort of delta V, they will not be equally spaced apart, however, essentially because of this 1 over R squared dependence that the electric field has. So we can define delta V as negative, the integral of the electric field over some path from some start point to some end point. And so essentially, if I want to figure out the potential for the point particle, I have to pick a path. And then I'm also going to pick a particular reference point that I'm going to use, where that's going to be where I declare V equals 0. Now, a Calc 3 course or an upper level analytic mechanics course will kind of go through kind of how you can do this very generally for various different kinds of line integrals, where you have to specify exactly which path you're taking and parameterize it and do all sorts of fun things. I will take the simplest path, that if I'm going from some starting point to some end point, I should have drawn this drawing a little bigger. So let me redraw this actually, or make it not as busy. Here's some Q. And essentially what I want to do is I want to go from some start point to some end point. And by the symmetry of the problem, I'm going to just take a radial path. So again, if I put Q at the origin, I'm going to start at some point, some distance RS away from the charge Q, and then I'm going to take a path that just radially moves out or in, doesn't matter, this is an arbitrary derivation, to some R endpoint. Essentially I'm going to do an integral that it's that red path. So I'm going to evaluate this over a radial path starting at R sub s, that'll be R start, ending at some other distance away from the charged particle, ending at R end, along a straight line and essentially I'm going to parameterize that path dr as I'm taking a bunch of little steps in a straight line that goes from R start to R end. So you just think of the direction of that red line on the screen. It also points kind of away from the charge, right, in the same direction as the electric fields. And you can imagine that arrow could also point from the charge in the same direction to R end, to this point of interest. So in this case, the path is just going to be dr, and it's in the direction r hat. It's in the same direction as the electric field, or it's anti-parallel if it's a negative charge. So in this case then, delta V equals negative integral from R start to R end of K, Q, and I'll just write R squared now instead of writing it as the magnitude of a vector, R hat, and that is dotted with dr R hat. So this looks like it involves, well, the K and the Q are constant, so I'll take those out. It looks like it's an integral of from R start to R end of 1 over R squared dr. And then it looks like that it also involves the dot product R hat dot R hat. But those are unit vectors, so it's the product of their magnitudes. They're both magnitude 1. Multiply the cosine of the angle between them. It's the same vector. The angle between them is 0. Cosine of 0 is 1. So that's just 1. So then it looks like all I have to do is do negative K, Q, integral of R start to R end of R to the negative 2 dr. Integrals of polynomials, I raise the power up by 1, divide by the new power, so I ultimately make this R to the negative 1, divide by a negative 1. That negative 1 cancels the outside negative sign, so this looks like it's KQ over R, evaluated at R end minus R start. All right, and then if I copy that back down, looks like I said delta V, which is V at the end point minus V at the start point, is KQ over R end minus KQ over R start. So again, you tell me how far radially away you end up and how far radially away you started. and they could be in opposite order. They don't necessarily have to be, going outward. This tells you how the potential changes, which again, that's what has physical meaning. Now it is often convenient. Again, I might want to write down a scalar function v everywhere in space so that I could easily kind of just plug in numbers to it, and then when I want to figure out what delta v is, rather than having to do this integral every time. So it's convenient to define v equals 0 at infinity. That's usually the convention that's used here. Right? Notice you can't use the origin, because then you'd be plugging in 0 into the denominator. And so, remember, going back to our definitions, maybe I'll just go back and show it real quick. Right, the idea is if we want to define a scalar function, we integrate instead from the reference point to some point of interest. So it looks like I'm going to call r start infinity, and then this is going to just go out to some arbitrary value of r. So then what we're going to do is we're going to let r start go to infinity, and we're going to let r end, we're going to call it r. Let that just be general. So then that implies, since, again, if we call r start our reference point, then by definition we're saying that v start is 0. So then we could say v start is 0 by definition. And then that implies that v, which is only a function of r, looks like it's k q over r. Because, again, if I use a highlighter to kind of show what's going on, right, this is 0 by, well, that was terrible. Don't write with a highlighter. By definition, and then this is 0 as rs goes to infinity. And then I'm left with this typical, or what's typically used, scalar function for a potential of a point particle. Though again, maybe this is just me being a stickler. When you see a book, like, no disrespect to the authors of this textbook, but it's very sloppy. When they say the potential of a point particle is this formula, I would say no. The potential of a point particle is this formula under the assumption that the reference point is at infinity. You might want to use a different location for the reference point. Great. You can come up with then a equally valid formula. But this one, of course, is the potential of a point particle with v equals 0 at r equals infinity. Right? R equals infinity is the reference point in this case. And so, if I were to draw equipotential surfaces, indeed, they would not be equally separated apart. Actually, we could even use PHET to do that. PHET, let's see, potential and electric fields, called something like that. Charges and fields, close enough. I think I can draw equipotential surfaces. If not, this is going to be a quick sidebar that's going to be a complete waste of time. So suppose I have some point particle here. There's a point particle. It creates an electric field that points radially away. And I might be interested in the voltage, which I think this is just color. Yeah, I don't like that. But I do believe, here we go. I can draw equipotential lines that have a particular potential. So this is using, so this it looks like it's assuming that if you just look at the value of v, it seems to be going to 0 as I get farther away. So it seems like they're using the convention. V is 0 out at infinity. It seems as they get closer, it blows up, probably up to some, I could make it arbitrary high if I had enough pixels. But maybe I want to kind of map the equipotential contours starting at 50, close enough, right? Maybe there's 50, then I want to go down by 10. So then I want to find 40, close enough. And I want to find 30, close enough. And I find 20, close enough. 10, we gotta go all the way out here. Close enough. Then I guess to go to 0, right, I have to go all the way out to infinity. So even just with 10, 20, 30, 40, 50, right, can we even get, maybe we get 60. Where's 60? 60, close enough, right? The idea being that notice that the equipotential contours are not evenly spaced. They could become more and more spaced out as you go out. So that if I were a charged particle, I forget what this is supposed to represent. If I were a charged particle and I went from, I guess ignore the arrows. Can I turn those arrows off? I guess not, now with the sensor. That if I were to go from, say, 10 volts to 20 volts, that seems like I'm decreasing my, I'm going, or I've increased my potential. I've gone from 10 volts to 20 volts. And then you can go back to the formulas and you should be able to convince yourself for a positive charge that should increase its potential energy, because I'm essentially acting against the direction it wants to go. Just left on its own, the electric field would of course make it go this way. Just like how gravity, left on its own, the thing will go from high potential to low potential. It will tend towards the lowest energy state in terms of potential energy. If I go against where it wants to go, that will increase its potential energy. But you could ask yourself, like for a delta V of 10 volts, how much kinetic energy, how much does the kinetic energy change for, say, a proton? And notice that, the distance over that which that work is done becomes squished more and more and more as you get closer. I guess I don't need to draw that. So there we got V from E. Of course, we should be allowed to get E back from V. That if I take negative the gradient of V, I should be able to get V back. And here I have to be a little bit careful with what I've been doing, because technically I've been working in a coordinate system called a spherical coordinate system. Given the spherical symmetry, I didn't write things down in terms of X, Y, and Z, but I've been writing things down in terms of R, how far radially away you are. Which it does turn out, in this case, and I'll elaborate on this in a second, this ends up just being negative dV by dr, and then it points in the r hat direction. Which notice, when I actually do that derivative, that seems like it's negative, and then the derivative of kq over r, a negative drops down, the r becomes an r squared, and then I'm saying it's in the r hat direction. Notice then that indeed we get kq over r squared r hat, which is exactly what we had started with for E. So when I write down that the gradient of V, let me just, a quick aside on coordinate systems. Cartesian is great, but sometimes Cartesian is not always the best way to do things, like in the case of spherical symmetry. If you have spherical symmetry, why not use a coordinate system that instead of X, Y, and Z, it's something that maybe utilizes the kind of geometry that you're dealing with. Like perhaps one of the coordinate systems should be not X, Y, or Z, but how far radially away you are from the center, if you're dealing with, say, a sphere. That's what's called spherical coordinates. The other kind of most common one is, if you think of a long wire, and we talked about the electric field around a wire, and it always pointed kind of radially away from the wire, but I could have the wire kind of go up and down as far as I wanted. That looks very much like a cylinder. where you can imagine drawing a circle around with the wire in the center of the circle, and then you kind of have a cylindrical shape kind of surrounding that wire. So there, the coordinates might involve something like how far away you are radially from the wire, and then maybe some angle that determines kind of where you are kind of in this direction, and then where you are height-wise along the wire. So there's Cartesian, kind of x, y, z, which is the most common. I guess, can I say that? I guess maybe the simplest is the way I'll say that. X, Y, Z. All of these systems are also orthogonal coordinate systems. What I mean by that is just a fancy word for the axes that I draw are all perpendicular to one another. And they do also obey the cyclic right-hand rule orientation, but don't worry too much about that. Save that for analytic mechanics. These are all perpendicular to one another. Cartesian is perhaps the simplest because when you evaluate derivatives on a Cartesian system, essentially you can just look at each dimension. Each dimension more or less is dealt with exactly the same. So for example, when you do the gradient of v, which might be a function of x, y, and z, that is just the vector that is the partial of v with respect to x, comma, the partial of v with respect to y, comma, the partial of v with respect to z. And throw a negative sign in front, and that's your electric field. There's cylindrical. Not how you spell cylindrical. There is cylindrical. Or sometimes the 2D version, this is called polar, where, let me draw the 2D first, where here's my Cartesian axes that, actually let me do those, let's see, I need another color. I'm going to do those in light gray because that's not what I want us to focus on. So there's y and x. Actually, I think I made it too light. That's okay. So then if I have some point here, I can describe the location of that point by saying how far in the x direction it is and how far in the y direction it is. That's Cartesian. Polar instead says how far are you away from the origin, and then kind of what angle have you swept, conventionally measured from counterclockwise from the x-axis. So the coordinate system that we have in this case, we use a different color, is how far away you are from the origin. That gives you the coordinate r. And then, so then one of the axes points in this direction. I'm going to call this the r hat direction. Actually, for cylindrical, we've been kind of using capital R. So I'll stick with kind of our lecture unit. But then if I want to think 2D, I still want a 2D axis where the other axis is perpendicular, like how x and y are perpendicular. So I define a new axis here, which I call the polar axis or the theta axis. And then they are perpendicular with one another. And so if you specify r and theta, that kind of uniquely determines where you are and your kind of overall orientation. The tricky thing is that you have to be careful about. Here, this is some angle theta. Is that if I want to do, so essentially then any point, so some function v or any point can be written in terms of r, theta, and then if you want to then include the z direction, there might be a 3D z direction here. Make it a little darker. There's y, there's x, and there might be some z direction into and out of the page. Turns out that the cylindrical coordinate system then kind of maintains that as one of its axes as well. So it sticks with also having z. So then you have an axis that points in kind of the radial direction, the theta direction, and then in and out of the page, which is the z direction. So then you can describe the location of a particle or a charge or whatnot by three different coordinates, r, theta, and z. And so then you might ask yourself, what if I want to calculate the gradient, which should give me a vector quantity that kind of points in the direction of, I guess, steepest ascent in this case. I guess we did talk a little bit about that earlier, but let me just recap because it's been a minute. These kind of arrows here where we're talking about kind of steepest descent, the gradient, you work this out in a Calc 3 course, the gradient vector is a vector that when you look at the magnitude of this vector, it points in the direction of steepest ascent. So again, for the electric field, if you throw a negative sign in front, the gradient, then points in the direction of steepest descent. And the thing you have to be careful about is that if I want to evaluate the gradient in this case, I can't just say dv dr, dv d theta, dv dz. For one, the units don't make sense. Two, right? dv dr, that's a potential divided by a distance, units of volts per meter. dv dz, volts per meter. dv d theta, volts per, and one of those dimensionless units. So it just has units of volts. I can't have a vector where the units differ. So you have to be careful in just defining exactly, when I move a little bit of theta, when I move a little bit of angle, how much distance am I sweeping out, right? If you imagine the tip of this pen, right? If I move a little angle theta, the tip of this pen is sweeping out a distance, this kind of arc. That's not d theta. Again, the units don't make sense. That arc there is r d theta, right? The length of the radius of this pen multiplied by d theta. So you have to take stuff like that into account. And then usually these are in like fronts of textbooks and stuff like that. So then this gradient ends up being dvd capital R. Then this ends up being 1 divided by r dv d theta. Notice there the units do make sense. Let me zoom in, sorry. The units do make sense. The first term is v divided by distance. The second term is now v divided by theta, so that's just v, but then 1 over r divided by distance. And then this is dv dz, also a distance, or v divided by a distance. And these are usually in like the fronts of textbooks or whatnot. You wouldn't be expected to have this memorized. But when you work in different coordinate systems, essentially the calculus, the expressions for derivatives are different depending on your coordinate system. In the vector calculus world. And then the last one I'll just point out is spherical, where again I might have my Cartesian axes of, I guess I'll stick with what I had up there. No, let me actually go back to what we usually do. So this is y. Z is usually here and X is here. Again, with spherical, I might want to talk about kind of one coordinate that makes sense. If I have some point here, one coordinate that makes sense is some coordinate that points from the origin radially outward to that location. And so we can define one axis as kind of the points in the direction from the origin to that point. That's the radial direction. And we can ascribe a value of r, right? Tell me if r is 3, that means I'm 3 units away from the origin, or what have you. Then there's now 2 angles I can describe. And this one you might have some intuition with, because it's essentially the same idea of like latitude and longitude. I can tell you where exactly we are on the surface of the Earth if I tell you a latitude and a longitude, which are technically 2 angles. Not physical locations, but give me 2 angles, that tells me where to go look on the surface of a sphere. if I then want to make it 3D, right, I could tell you a latitude, a longitude, and then how far away from the core of the Earth I am. So if I say, latitude, longitude, and then 4,000 miles, which is roughly the radius of the Earth, that kind of tells me a location on the surface. But if I say latitude, longitude, and then specify r is equal to 1,000 miles, right, then I'm kind of somewhere probably in the mantle inside the Earth. So there's kind of two angles that can be used here, the azimuth and the altitude. So I can imagine projecting a shadow of this point, or if I shine a light down on top of it, that projects a shadow. And then this red line, this dotted red line, has its shadow as well. And I can define one of these angles as going from the x-axis out to here. And I might call that theta, since that kind of seems to match the polar definition of theta. You go counterclockwise from the x-axis. But then, that kind of then tells me how to sweep around in this direction. But then I kind of also have to specify where I am, so that you could think of as latitude. But then I also have to specify longitude, or what's called the altitude, which then is just the angle from the z-axis down to this line. Maybe I'll call it phi. So then theta, call azimuth, or again, you can think of that as latitude on the Earth, and then phi is altitude, or longitude on the Earth. So then I can specify, say, a function, v, in terms of r, how far from the origin you are, what's my altitude, and what's my azimuth, and then what's my altitude. And then those also define your axes as well. So essentially, it's kind of hard to draw. But essentially, there's kind of 3 axes that then get drawn here. This is kind of going into the page a little bit. Sorry, this is very messy. Computer drawings can do a much better job, but then all of these are kind of at right angles from one another. That's not too bad. But then again, if I want to then take a derivative of this thing, oops, not red. If I want to take a derivative of this thing, 2 of those are angles. So the first term does end up being dv dr, but then the others can't be dv d phi and dv d theta, because that doesn't give me the right units of volts per meter. And so, without proof, admittedly, you can derive this to be 1 over r, then dv d theta, and then the other one becomes 1 over r sine theta dv d phi. And again, we probably won't do very much with this, but you should be aware of it. You'll definitely see this in future courses. So essentially, you do the calculus. The calculus you do depends on your coordinate system. Cartesian is kind of the most simple and straightforward, but then sometimes cylindrical and spherical utilize symmetry in a way that makes your life a lot easier, as long as you know how the vector derivatives change. And then similarly, integrals can also kind of take new forms as well. Rather than integrating just dx, dy, dz, you might want to integrate over r, theta, and z. But you have to just be careful with those integrals. Maybe we'll see that later on. Maybe I'll work that in later on. I don't want to throw too much new stuff in right now at the beginning. Okay. Still got some stuff to get through. Let me do an example of the potential across 2 plates. The 2 plates, again, are going to play a very important role for us, especially in the next lecture on capacitors. So suppose I have 2 plates that are separated by a distance d. The left plate has a positive charge on it, the negative plate has a negative charge on it. such that there's a uniform electric field in between them. Just draw that as straight lines. So there's some uniform field, I'll say E naught, and it's pointing towards the right in the x direction, the way I've drawn these plates. And the left plate, we'll say, has some potential V left, and the right plate has some potential, which we will call VR. And we're going to specify that VR is 0. Essentially, I'm defining that to be, kind of my reference in a sense. I'm saying whatever the potential is, if I want to give a unique value, I'm going to say it's 0 at the right plate. Then I'm going to ask what is it on the left plate in terms of the electric field, presumably the distance separating these things matters. What is the connection between the potential difference between two plates, the electric field, and the separation? And again, you might say, it seems, maybe like I'm heavy-handedly, doing something by saying VR equals 0. But again, it's only delta V that matters. Right? Really, what I care about is the delta V across the two plates. So I could call, right, VB, 10. But when I still get a delta V, it's going to be the same regardless of what I call V sub R. So then V sub L is, by definition, negative the integral of the electric field dotted with some path where I start at the right and end at the left plate. So, and I can take any path that starts at the right plate and ends up at the left plate. I can remember because it's path independent. I guess that was 2 lectures ago. So I'm going to choose a pretty simple path. I'm going to let dr be, I'm just going to move in a straight line horizontally. So my path looks like it's going to be nothing more than, well, actually, I can be even simpler about this. Since the electric field is a constant, right, this is the same thing as negative E dot delta R, where then this is the bulk displacement of, right, I don't have to do that integral if E is just a constant, because then I'm just adding up E dot dr over, right, again, over any path, but then I can use kind of, it's going to ultimately just be my net displacement. This is kind of nice. And let's see, I want to be careful, again, to emphasize that's really a delta V. So maybe I will actually just get rid of this. In which case, then this integral is delta V, which is going to be VL minus VR, right? And end minus start, which I'm going to call delta V, is by definition this integral. I know that the left plate is going to be at a higher potential than the lower plate. Think back conceptually what we talked about with the connection between electric field and potential. And in this case, then, it looks like I can write down that delta V is negative the electric field, but we said the electric field is E naught in the x direction. And then my net displacement, where I moved a distance d, but I moved to the left. I moved, so you can imagine moving horizontally to the left. It's going to be then the dot product with, looks like I want negative d to the left, right? So then I have negative d times x hat. The x hat, where I'm moving kind of horizontally, negative, I'm moving to the left. The amount of distance I moved, d. So I essentially then have drawn a path where I start here and then end here. And so notice I am going against the electric field. Now it looks like this is just the negatives cancel. It looks like it's E naught times D. Then I have x hat times x hat, or x hat dotted x hat, which is then just 1. So it looks like I have delta V is E naught times D. So for the potential difference across two plates, conceptually knowing that the positive plate is held at a higher potential than the lower plate. What is that difference? The electric field times their displacement d, or the distance between the two plates, d. So again, if I wanted to say the negative plate is 0, then I could say the positive plate is at a potential of E times d. So I think then here it's kind of worth talking about different kinds of notation you will see, which I personally find very confusing, right? So we kind of just derive that delta V is equal to E times D. But again, this delta V, right, was, we started at the negative plate and went to the positive plate. Again, to be consistent with what we were saying before, right, we went against the electric field, so our potential increased, final minus initial, or again, saying that the positive plate is at a higher potential than the negative plate. You will see this sometimes written as kind of VLR equals E naught D, which kind of also still matches our notation if you think of this as the kind of delta V going, because when we had subtrips, we always kind of wrote it, when we think Coulomb's law and forces and electric fields, we always said like to blah from blah, if you go back to those lectures and look, and this, you can think of it kind of the same way, delta V going to the first letter L from the second letter R. So again, going to the, in this case, the left plate, which is the positive plate, from R, the right plate, which was the negative plate. Or again, it's saying the left plate is at a higher potential. So again, it's just notation that typically people are consistent with, but sometimes books aren't, and it causes quite a headache. Because again, when we say, it kind of looks like we're saying that the value of the potential is equal to E naught times D when you look at something like this, because there's no delta. But I think they're implying a delta when you write it like this. Or again, you can think of it as the right plate is 0 and then the left plate is E naught D, or the positive plate is E naught D. But yeah, same thing is true actually for kind of spherical coordinates too. These two angles, depending on where you look, are sometimes swapped. Sometimes this angle is called theta and this angle is called phi, which is a real headache. Anyway. Quick numerical example. What is the max voltage between two plates that is separated 2.5 centimeters before you get dielectric breakdown? Before dielectric breakdown, which, remember, we said occurs in, as long as it's air in between the two plates, we said occurs when the electric field is 3 times 10 to the 6 volts per meter, or newtons per coulomb, which you also showed in class are equivalent units. Well, that's not too bad, because we know that the kind of potential difference across the plates is equal to the electric field between them times the distance. So in that case, it looks like then just delta V is 3 times 10 to the 6 multiplied by 0.025 meters, and then the unit will then be in volts, and this looks like it's about 75 kilovolts. Before you would expect arcing or sparks in between the two plates, or two kind of conducting pieces. All right, so actually that one we will need again, so I'm gonna highlight that. But then also be aware that you might see it kind of written like this as well. But really it's saying the same thing. Now here's another example where, again, I just find the notation kind of sloppy. Though again, if you know kind of physically what's going on, that's okay. So suppose suppose your car or your vehicle it's a battery operated car and it has a 120 volt battery. That's usually how you will see it explained. How much charge must be drawn or moved through the battery to accelerate your, let's say, 700 kilogram car up to 25 miles per hour from rest. 25 miles per hour, which is about 11.2 meters per second from rest. So here again is where I find the notation a little sloppy, in that as the physicist I'm thinking it's only delta V that has any meaning. So what the heck do you mean when you say you have a 120 volt battery? What's the reference point? Of course, what they mean is that the potential difference across the battery is 120 volts. So that if you have your battery, which has a positive terminal and a negative terminal, what this is saying is that as you go across the terminal from positive to negative, there is a potential difference of 120 volts. Or again, you can think of it as the positive terminal, or if you want, you can call the negative terminal 0, the positive terminal 120. Or you can call it the negative terminal 120, then the positive is 240. The difference is 120 volts, which again is what has any physical meaning. And then it's usually kind of problems like this, where sometimes if you're being very meticulous and careful about what the signs of things should be, sometimes it gets a little confusing, but you can kind of reason out kind of what's going on in terms of the signs. Because again, if you have some sort of battery, it's connected to something that is going to do meaningful work, which is going to then accelerate your car. So charge is kind of pumped along the circuit. It's given some energy from the battery. That's the whole next unit. It then goes through something that will then get make the wheels start turning, and there's some sort of work that's done, and then when it returns to the battery, and then the charges are kind of renewed with some new energy to then kind of chug along and pass along to things along the circuit. So if the question is how much charge must be drawn to accelerate a 700 kilogram object up to 25 miles per hour from rest, we can connect we know that when a charge moves through a potential difference, that results in a change in the charge's potential energy. So again, you can think of if you have some sort of amount of charge that then goes through a delta V, the potential energy of that charge changes. And of course, we're thinking that we should the charges should gain some potential energy in a sense that it can then go and give to something else to do meaningful work. But here's again where it kind of gets confusing, because a change in potential energy, it seems like what that's saying is inside the battery there's some sort of change in its potential, but then once it leaves the battery, you might say, well, this doesn't make it does what does potential energy mean anymore if you're outside the battery? So again, what you can think of this as trying to say is that this, for batteries, this kind of Q delta V is the energy kind of extracted from the battery to be used to do meaningful work. So yeah, thinking about like a potential energy is kind of confusing, because you might think, potential energy of what? The charges in the battery, but then outside the battery, what's going on? That's okay. I would think of this as just kind of the oomph, that it gets from the battery, that it can then go do meaningful work. There's a more technical term called the electromotive force, which is also kind of a weird notation because it's not really a force. But I like that if I try to say EMF out loud, it kind of sounds like oomph. So I give some oomph to the charges for them to then go march along and do some meaningful work. Again, we'll come back to that in the circuits chapter. But there's some sort of energy extracted, and then the charges then have that to then pass on to something to do meaningful work with. So how much work does it take, since we're thinking about energies? This is not a kinematics question, right? For one, the kinematic equations, if you want to blindly start plugging things in, the kinematic equations assume constant acceleration. I technically did not say you uniformly accelerate up to 25 miles per hour. I just say you accelerate from rest up to 25 miles per hour. So we should think of this in terms of energies. So if I get Q delta V energy to do work with, how much work does it take to change my kinetic energy from 0 to whatever it is if I'm moving at 25 miles per hour? Well, I know at the heart of all of this is the work energy theorem. I know that the work done is equal to the change in kinetic energy. So then, if I think of the change in kinetic energy, and if I start from rest, that's 1/2 mv final squared minus 1/2 mv initial squared. But again, if I'm starting from rest, that's 0. Right, I need to do that much work to go from rest to 25 miles per hour if I plug in 25 miles per hour for V, and I have a value for M. Work is an energy, right? It has units of joules. Where did that energy come from? Essentially, the energy I got from the battery then goes into the kinetic energy I then can, or I can go into do work that then changes my kinetic energy. So I know delta V, 120, I know M, I know V final. You can solve for Q. I get 359.6 coulombs. Oh, sorry, 0.36 coulombs. Fun. I still want to say something about equipotentials and conductors, but let me very, very, very quickly say something about superposition. And I'll skip over the continuous charge distribution example. As you might imagine, we've talked about superposition in terms of forces, in terms of electric fields. Same sorts of arguments. You can then talk about the superposition of potentials. If, for example, I have several point particles, Q1, Q2, Q3, and then there's some point of interest that I'm curious about. Right, these are all separated by different distances. And I could evaluate the potential at P as the sum of the potentials at from each of the points. Each charge, which again, really it's that each of those charges create an electric field. Each of them have their own agent that they then kind of shoot out into space. They each have a potential. You can associate a potential with each of them. I can then talk about the potential at a given point as the sum of them. So, for example, if I say the V of a bunch of points, then would then be kind of the sum of K Q sub I over R sub I, summing up over all the points. And typically, to make your life sane, right, if you're doing a bunch of points, right, probably should use the same reference point for all of them. But again, you don't have to, because again, it's only differences that matter. But I don't know why you wouldn't. Anyway. All right, yeah, then I was gonna sketch it out for a dipole, but maybe I'll make that a class problem instead. Because I do want to say something about equipotential conductors and a little Gauss's law redux or review. I want to try to argue that if I have a conductor that has some excess charge on it, I can ask questions like, where is all that charge on the conductor? I can then also ask, what can I say about the equipotential surfaces on that conductor as well? So, and to do some of that, we could have done some of that when we did Gauss's law, but I'm going to do it now. Suppose I have some sort of conductor, and this is not necessarily a shell, it can be a solid object. In fact, I'm going to assume it's a solid object. So we have some conductor with some sort of excess charge on it. All right, so there's some charge Q, excess charge Q, that's on this conductor. If I place that excess charge on the conductor, where again, remember the idea of the conductor is that we kind of defined it to be, an object where charges can freely move around. Those charges are going to then kind of freely move around, but they're going to, if I put a bunch of positive charges on the conductor, they're going to try to all get away from each other. They'd rather be spread as far apart as they can. Eventually, they're going to reach some sort of equilibrium. So the kind of Q charges move around and eventually establish equilibrium. Once the equilibrium is established, once in equilibrium, where is all of this charge? Is it uniformly spread throughout? Did it all go bunch up in a corner? Where did the charge go? On the assumption, which could be tested, right, that when you put some excess charge on the object, it eventually reaches some sort of equilibrium, which means that none of these charges are moving around. That's a statics problem. Particularly with statics, the net force for any one of those charges were to be 0. So again, let's remind ourselves, equilibrium, particularly static, implies that F net is 0, for each of the charges. Else, if it wasn't, be compelled to move. So let me pick some arbitrary location inside the conductor. And let me draw kind of random little Gaussian surface somewhere that's entirely within the conductor. So this is some sort of closed surface entirely inside the conductor. All right, and it doesn't matter what shape it is. I could draw a little sphere or a little cylinder. I'm drawing some little arbitrary shape that's entirely inside the conductor. It's not piercing through the edges of the conductor, or it's also not along the surface of the conductor. So it's entirely inside. Since it is a closed surface, I know that by Gauss's law, this better equal, right? If I calculate the flux through that little red surface I've drawn, that better equal the amount of charge that's inside that little red surface divided by epsilon naught. And so then we can start to think about what's going on. The charges are in equilibrium. And again, we're asking ourselves, where are the charges? Charges are in equilibrium, which means F net equals 0 for each of the charges. But then what causes these forces that could act on the charges? Well, those must be electrostatic charges, or rather, it must be electrostatic forces from the charges. So we know then that the sum of kind of the Q sub I, maybe E sub I, maybe, right? That would be the kind of the net force better equals 0. These forces are arising from interactions with the other charges through their electric fields. But if we're saying that's 0, if you think about it, that must imply then that there is no, actually, let me be careful. I wrote this kind of sloppy. For a given charge Q, there's no net force, and that Q times all the electric fields that it might be interacting with has to add up to 0. Or if there's one charge, or I have a test charge, the net electric field it feels is what then translates to a force. But then this says that if this better add up to 0, then that means the electric field is 0. Else it would not be in equilibrium. Right? There can't be an electric field at any point along, wherever the charges are, there cannot be an electric field, because if there were an electric field, a net electric field, that would then naturally cause a force. That force then would cause an acceleration. That doesn't seem like an equilibrium position. So, in that case, if there's no net force, that means there can't be any net electric field. And again, the argument there is equilibrium. Equilib. But then if there's no electric field at any point, kind of along the surface, or wherever there are charges, then really, by Gauss's law, this is implying that Q enclosed equals 0 as a result. If there's no electric field, then there's no electric flux. If there's no electric flux, then there's no charge enclosed. So the idea that I've essentially made two arguments here. So the equilibrium argument I'm essentially implying that if everything is in equilibrium, there cannot be an electric field inside the conductor. This must therefore imply E equals 0 inside the conductor. Else the charges would be compelled to move. If the electric field is 0 inside the conductor, then that means Q enclosed is equal to 0 inside the conductor. At least for that particular Gaussian surface I drew, that little red blob I drew. For that particular blob, there can't be any charge inside that blob. But then I could draw a different blob elsewhere and make the same sort of argument. I would say there's no charge inside that blob. Then I could make a third blob where I actually kind of connect the two, so it's a bigger blob. And as long as it's all still inside. Right? Or I could go back up to this drawing and I can make a Gaussian surface that is essentially the same as the conductor, but it just kind of stays just inside the surface, in the same surface. Right? It's the same kind of shape and size as the conductor, but then the Gaussian surface is essentially everything that is the entire conductor except the surface. Well, again, we can make the argument that the electric field is 0, so then the flux is 0. So then there can't be any charge inside that surface. But then that surface essentially was the conductor, or at least the inside of the conductor. So then this kind of generalizes to say that all the excess charge rather, all the charge Q must then reside on the surface. Where does all the charge go? The charge has to go, red and red, terrible idea. All the charge must then end up on the surface. This is a Gauss's law argument. Essentially, if I have a big copper ball and put some charge on it, all those charges will go on the surface, which kind of intuitively makes sense if you think of the idea of, they're trying to get as far away from each other as possible. But they don't reside inside. The electric field actually goes to 0. This can be important. There's these things called Faraday cages that essentially, when there's excess, essentially you can imagine a big cage, which is a conductor, and if there were things inside, essentially, if there's charge on the cage, it will orient itself more or less to ensure that the electric field within it is 0. So that if instead of a cage, that's maybe the outer shell of your computer laptop or whatnot, this can be very important because it can protect the inside electronics from ever experiencing some sort of strong ambient electric field or something like that. Obviously, pending some sort of extreme situation. Okay, so this was kind of a Gauss law argument. All the charge must reside on the surface, right? The charge can go anywhere in the conductor, it will go and hang out on the surface. So then, what's it doing on the surface? So here's my conductor again, some sort of arbitrary shaped blob. And I'm essentially going to pick a little area and zoom in. So I'm going to pick this little area right here and zoom in. So if I were to zoom in on that area, here's kind of my blue window, where I've zoomed in on just the little piece of surface there. I've zoomed in so far that essentially I'm looking at a flat sheet. And if it doesn't look flat, zoom in even more. There is charge that is kind of distributed itself along the surface. It might not be uniformly over the surface, unless there's symmetry. Like if it's a big ball, by the symmetry, it makes sense that all the charge should be spherically symmetric on the surface. But if it's, something like I've drawn where, there are some parts that are jagged and some parts that are not, the charge distribution on the surface will be uneven, but nonetheless, it's all hanging out on the surface. On the surface, there is charge, so I expect there to be an electric field. Right, there is charge. So also an E field. But again, by equilibrium, if the thing's in equilibrium, then those charges have found a place to hang out on the surface, and then they're just sitting there. So if there is an electric field, right, that has to go just a nanometer above the surface, right, I would expect to feel and see an electric field from those charges. But the charges are in equilibrium, so they can't be moving around one another. So by equilibrium, E must be perpendicular to the surface. Again, if I had a surface where there was some charge here, some charges, but then there was a electric field that was not perpendicular to the surface, then the component of this electric field that points parallel to the surface would compel these charges to move. And again, that doesn't seem like equilibrium. So by equilibrium, the electric field must be parallel to the surface. So if we were to draw the electric field, it's going to be pointing directly away from the surface. I can actually even use Gauss's law to say what that electric field is based on the local charge density. Like there's some local 2D charge density, which I'll call sigma. I won't put sigma naught, because again, it's not necessarily a constant everywhere along the surface, but there's some dq by dA, charge spread over an area, and it has some local value here on the surface. And then that charge then is creating some sort of electric field that then is pointing perpendicular away from the surface. We could then do this by a Gauss law argument. So I could draw a little cylinder. So a cylinder that has a tiny little bit of height, then it goes down and kind of pierces into the surface, and then underneath the surface there's the rest of the cylinder. Essentially, just a tiny little pillbox that has some kind of cylindrical side, but then two flat tops. On the top, or on the upper top, right, there's an electric field that's pointing kind of out of that surface. The electric field inside, we already said is 0 on the previous page, right? There's no electric field piercing through the bottom top. And then we've also made the argument that the electric field is vertical, so there's no electric field going through the sides as well. So again, by Gauss's law, kind of the flux through that little pillbox better equal the charge enclosed divided by epsilon naught. The flux going through the pillbox, right, there's nothing going through the sides, there's nothing going through that bottom part, it's only kind of going through the top. And again, if you think of when we did the infinite sheet, I've essentially zoomed in so much that this kind of looks like an infinite sheet, right? And again, if it doesn't, zoom in even more. So then this is some value of the electric field times, this would be an A, sorry, not dr. I'm used to drs, right, from potential. Flux over an area. But then the area of that little top is going to be then pi times whatever its radius is squared. Right, so again, if the pillbox has some radius r, then it pierces into the surface. And then the part that's inside also has radius r. Then the charge enclosed, if I zoom in here, if the charge enclosed is that there's this little piece of sheet right here that the pillbox is kind of clipping. Let me try to redraw it actually a little bit bigger. Essentially we have big old sheet. And then I have the top of the pillbox. Then it goes down. It eventually pierces into the sheet. And then it has the part that is beneath the sheet. Essentially, it is this little part right here. That little, circular disc of sheet has some charge. Particularly the charge in this case is going to be whatever the local charge density is, charge per area, times the area of that red disk. Then if I zoom back out, the charge enclosed looks like it's then sigma times pi r squared divided by epsilon naught. And then notice that the pi r squareds cancel out, which is very helpful because that was kind of that was arbitrary, right? This was this little Gaussian pillbox I dreamt up. Why should the size of it matter at all? So then it seems like the electric field just off the surface and on the surface is equal to the local charge density, whatever that is, divided by epsilon naught. And it points in what direction? Points away from the surface. Or I guess away or towards, depending on if Q is positive or negative. But it's perpendicular, right? That's the point. It's perpendicular to the surface. So then bring this all together. Where'd potential go? If the electric field is 0 inside a conductor, then inside a conductor, delta V, or how your potential changes, which is defined to be your path, this kind of E dot dr integral. But if E is 0, then delta V is 0. I could start and end at any point inside the conductor, and my delta V doesn't change. So the entire inside of the conductor is so entire inside of conductor is, if we want to think of it as, is at the same potential, is at the same value of V. Again, define your reference point. We could call it 0, right? Essentially, that's what grounding is. When you ground a conducting object, essentially you're making it match the potential of the Earth. And since then this conductor then kind of has the same potential, you've grounded it to match the potential. There's no delta V between the Earth and likely you standing on the Earth and the object. But we can also say something about the surface. On the surface, E is perpendicular to the surface. So if I were to calculate some delta V along the surface, which means I pick 2 points on the surface and I move from one point to another, but I'm always along the surface, the entire time, then that also has to be 0. Because E is always perpendicular to whatever direction you're moving. So then, the big takeaway, final thing to say, and we'll save the examples for class, is that an entire conductor, or the entire conductor is an equipotential surface. Conductor is recording for too long, is an equipotential surface. No matter where you are on the conductor, you could be on the surface, you could be inside the conductor, And the entire thing is at the same potential value. There's no delta V no matter where you start and where you end on a conductor. And again, the idea of grounding is to assure that that delta V, essentially that the V, if you want to associate a value of potential for the conductor, it's the same everywhere. If you ground the object by connecting it to the earth, then it essentially becomes essentially the earth, you can think of it as a giant equipotential surface. The wire that's connecting it is, if it's a conducting wire, that wire is an equipotential surface. And then if it touches this conducting object, which is an equipotential surface, they all become the same potential. They all have the same value of the potential. So the idea of a conducting wire, when I connect the surface of a battery through with a wire to some other object, that wire essentially becomes a long equipotential surface from the battery to the object. Where if I can establish, some reason for things to move, they could do so without having to do any work, without any work being done. So, big conceptual takeaway that will be important here. So again, let's recap. What can I highlight? I guess the conductor is an equipotential surface. And by that I mean the conductor, which is its own surface and the insides, is all at the same potential. Maybe I'll write that, right? When I say equipotential surface, right? All at same potential. There's no delta V anywhere. Okay, all right, and then we actually have an expression for the surface electric field. And we'll do an example that actually will kind of motivate why, we might have been saying, you might have heard us say either in lab or in lecture that, if you have kind of kinks in an object, like a or like sharp, what am I trying to say? If you have an object that's kind of like, a flat sheet of paper, but there's kind of a spike in it, or it's bent in a certain location, kind of locations where things are bent or kind of come to a point typically have higher charge densities and stronger electric fields. So like a lightning rod, which is just a rod, which kind of has a very sharp point, can create a very strong electric field compared to if it was kind of a big giant smoothed out ball. And we can kind of work through that example together in class. But lots of good things here. Maybe worth kind of doing a twice, watching it again at 1.5 speed at some point. But I think this will kind of wrap up our discussion of potential after doing some more problems on this stuff.